All right, good afternoon and welcome everybody to Intro to Space Navigation Spring 2025 Lecture 21. It's getting harder and harder to bookkeep these and not make a mistake, so I just refer back to my OneNote page to make sure I'm reading off the right number. So we are in Lecture 2 of 3, so we're in the middle of our Kalman filter unit. And as a reminder, last class, we did Kalman filters part 1, and we talked about how we use Kalman filter. Kind of the metaphor that I use for Kalman filters is whether or not you trust your friend's Google Maps skills on a road trip. Basically it. So you'll have your own mental model of where you are, and then you'll have someone telling you where you are, and you've got to use your judgment to decide, are you right or are they right, or is it going to be some sort of compromise, right? And that's really what a Kalman filter is. Your computer has a decent dynamics model, it should be able to simulate where it is to a great degree of precision. But the thing is, you never know exactly where you are. You never really even measure your full state. You measure some aspect of your state, right? If you take a line of sight direction to a known landmark, that gives you 2 degrees of freedom out of your position. It tells you nothing about velocity. So you get some information, but it only buys down some of your error. And then you've got a noisy measurement, so you need to be able to fold in new information as it becomes available, while keeping a running tally of like where you think you are in space, right? And that's the purpose of a Kalman filter. So there's 2 steps to a Kalman filter, and this is, as you're marching forward, this is right foot, left foot, right foot, left foot, and that is propagate and update. And I realize other people use different nomenclature here. I say propagate, update. There's some kind of fields that refer to Kalman filter as prediction correction. So there's the predictor step and the corrector step. It's the same basic idea, right? There's where do I think I am based on the dynamics? Where do I think I am based on the measurements? And then you need to choose which one do you trust every time a new measurement comes in. And so we talked about how we propagate our dynamics. So we assume that our dynamics follows a linear measurement model. So the future state, or I should say the derivative of the state, is just some matrix F times the current state plus noise. And we didn't really talk as much about measurement last class. That's actually what we're going to focus on today. And we said that you can propagate not your state, because you don't actually know your state, but you have the expected value of your state. You have kind of your best guess. And you can propagate that forward using the state transition matrix, or there's other methods that you could use. And then you can also propagate your covariance forward using some combination. And boy, this was a gnarly derivation, wasn't it? I promise today is not quite as bad, I think. The covariance propagates according to one term, which is the state transition matrix, and another term, which is the integral of all of the noise. Right? So we're integrating the effective noise over time. And the covariance, right? If you integrate noise over time for your state, then you might say, well, that's supposed to cancel out. And it does. You'll notice there's no noise term in your state propagation step. We say, well, sometimes the noise is going to put us in the negative, sometimes it's going to put us in the positive, but in aggregate, when you integrate everything, it should cancel itself out. So we ignore the noise when we propagate the state. But when we propagate our state uncertainty, which is our covariance, you absolutely need to take into account the noise, and it does not cancel itself out, because as you're propagating, every single time step, you're just a little bit less sure of where you are. And that never gets better until you take a measurement. And then as a reminder, we have this kind of diagram that I refer back to here, which is you've got your spacecraft, you've got some sort of nav sensor, your uncertainty is going to grow. The error bars on your state are going to get wider and wider and wider until you take a measurement and they're going to plummet. But they're not going to plummet to 0 because you're still not quite sure. You're just more sure. And then that will tend to get worse again, and so on and so forth. It makes this kind of sawtooth graph. If you look at publications on the performance of Kalman filters, a lot of them will have a sawtooth plot, something like this, which shows its uncertainty over time. Unless it's getting measurements in more consistently, then that sawtooth gets very low, kind of a smaller oscillation. But in general, some type of behavior like this is what we expect from a Kalman filter. So you say, okay, Paul, we talked last class about, and then we also have an alternate method for state and covariance propagation. Ooh, that was a gnarly one too. But when we get to the end of this, we say, okay, here are 2 different ways of telling what is your future state and covariance based on your past state and covariance and your dynamics model, which is typically captured by this F matrix, or your phi matrix, which is a function of F. Okay, so then that's the propagate step. Today is all about the update step. So this is Kalman filters part 2. Let me see. Yeah, Kalman filters 2. Part 2. And we're going to be spending most of our time today on the measurement update step. Okay, so we begin with the measurement model, which is nice and linear. Which is y with noise is, you know what, I'm going to drop the of t notation for now, because y happens in an instant. And so y is going to be h times x plus nu, okay? Where nu is our measurement noise. Now this should look familiar. This is the exact same model as when we went all the way back to our first lecture on estimation theory, y equals hx plus nu. It's the same thing, right? We're saying that our measurement, which could be a scalar, could be a vector, is just a matrix multiplied by our state plus some noise, where that noise is a Gaussian random vector with, so it's Gaussian, 0 mean, and a covariance of R. I realized there was some confusion on homework 2 because there were 2 covariance matrices floating around. There's R and there's P. And I found that when I quizzed people, it was relatively difficult for people to tell me the difference between R and P. And I want to be abundantly clear that R is how much you don't trust your measurement, and P is how much you don't trust your state. And so we can actually compute P. Do I have it here, or no? I think I have it in here. You can compute your covariance. Here's the equation, right there. Your covariance, P, how much you don't trust your state. And maybe I'll even add this to the notes here. How much we distrust our state is a function of R, which is how much we distrust our measurement or measurements, and H, which if you look at the way H is set up, H captures our measurement geometry. I've heard of H referred to as the measurement geometry matrix, or sometimes as the measurement sensitivity matrix. But when we actually set up our equations, H is typically, you know, your beacon locations or your line of sight directions, something about the geometry, like the vector math of where you are in relationship to the things that you're measuring, is H. Right? That's why we said that your problem becomes unobservable if H loses rank, because that means that you're not measuring as many directions as you need to get your full state. So I just want to be abundantly clear. That's the difference between R and P. And then there's Q, the new kid on the block, which is how much we don't trust our dynamics. Right? So how much you don't trust your measurement, how much you don't trust your dynamics, how much you don't trust your state. There's 3 of them now we got to keep track of. Okay. So the measurement covariance is the expected value of, and this is by definition, measurement minus expected value of the measurement, and then measurement minus expected value of the measurement transpose, like so, which is the same thing as y, or sorry, instead of y, we'll say hx plus new minus, remember the expected value of our measurement is that we expect the noise not to matter, right? Noise has a mean of 0. So on average, this noise won't matter. So the expected value of y is just hx. This is y. Sorry, I did it again. Hx plus new minus hx transpose, which cancel, 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 cancel. Our expected value of new transpose is our measurement covariance matrix, R. Okay, so this is where, okay, I have to apologize. We're going to do a change in notation for this lecture because we're running out of symbols. So I'm going to make a really big note. In this derivation, hat, so like x hat, for example, denotes a filter estimate. Not necessarily a unit vector. So we do this instead of writing EST for estimated, right? Just saves us some time. So we're also going to use this notation. So x hat minus is the estimate of the state after propagation and before update. So to go back to our graph from lecture 20, right, we have our uncertainty. It's getting larger and larger and larger. And then in an instant, so technically in the same time instant that you get your measurement or that you process your measurement, your uncertainty is going to plummet. And your state, your estimate of your state is going to change. So in an instant, we're not propagating forward. We're not saying at the next time step it looks differently. We're saying all at once we have a new covariance and a new state. That's why we introduced this plus and this minus notation. So x hat plus is the estimate of the state after update and before propagation. So this is after we do our update. So today's entire lecture is how to turn x hat minus into x hat plus and p minus into p plus. That is the update step. But then your x hat minus and your your x hat plus and your p plus still need to be propagated forward. So then we go back to the last lecture, propagate, update, propagate, update. Okay. So we define x hat to be an unbiased estimate of x. And we can describe error as E minus is x vector, so truth, minus our estimate before the update, where the expected value of E minus is 0, right? On average, we think that while we might have some error, there's no bias. So on average, we're assuming that our estimate is correct. And then E hat plus is x minus x hat plus. So this is the error after the update. It makes sense that we're going to want to minimize the error after the update. So maybe you can kind of see where we're going with this.
Paul, are
So
those E hats or E vectors?
these are E vectors. Yep. So in this case, before I realized I probably need to touch up the notation in this lecture. Before we had E hat was a line of sight vector. And now we're saying that X hat is an estimate and then E vector is error. So might need to touch that up. So my apologies if today is confusing, but those are not line of sight directions. Okay. Bop. In this case, it's E for error. So I'll make a note. These are not line of sight directions. Okay, so moving on to the next page here. We will construct a state update of the following form. So we're going to say that our state after we update is our state before we update plus, bear with me here, k times y minus h x hat minus. Okay. So let me explain what is going on here. So this is new. This is old. K is some gain. So if you took ModCon, you're thinking like KP, KI, KD, right? Your PID controller gains. Maybe that's giving you flashbacks just even using those words. But K is going to be some sort of gain, and I'm just going to leave that as a big old question mark for now. And then all of this is our residual, or our error, right? So if we were absolutely correct with our best estimate of our state, well, here's kind of the question, right? Either your state is wrong or your measurement is wrong, right? So if you have some situation where your measurement minus hx, so hx is going to be our expected measurement, and then y is our actual measurement. The difference of those is going to be your residual, your error, right? So this is kind of like your feedback error. And then K is going to be some sort of gain, and we'll talk about the gain later. The gain has to do with how sensitive you are to error. And then we say that whole term adds on to the old estimate of our state to give us the new estimate of our state. So it stands to reason that if your measurement is exactly what you were expecting to see, then the whole second term is 0, and you just pass through. Your old state becomes your new state. If you are driving down the highway and you think you have driven 100 miles, and your friend pulls out their phone and says, "Hey, we've gone about 100 miles." You go, "Cool," and there's no update, right? It's only when you pull out their phone and they go, "Oh, we've actually done 150." You go, "Oh gosh, do I trust you?" All of a sudden, there's some residual, and then this gain term determines: are we going to stick with the old one, or are we going to stick with the new one, or how are we going to handle this, right? So we'll talk about where K comes from in the future, but this is how we're going to handle our update. And I'll say note. This is the Kalman filter. So the magic happens right here. Okay. So all of our work on propagating was dumb. Not dumb as in a waste of time, but it was automatic. Right? So a computer can just take a set of equations and keep solving them over and over again. This is where a decision has to be made. Okay, so how much should we trust X? How much weight do we give to perceived error? And so I'll say K is the Kalman gain. And if you just look at the equation, it has to be a matrix. It's not a scalar. It is not simple. And it does the heavy lifting. Okay, so let's ask this question. So what we're building towards is, first of all, how do we update our covariance? So this is our state update. How do we update our covariance? And then where does K come from? And then we're just going to summarize, and then that's basically the end of at least the linear Kalman filter discussion. So it'll probably take us about a half hour to get through that, and then we'll take a break. You might say then, oh no, Paul used the phrase linear Kalman filter. Is there a nonlinear Kalman filter? Spoilers, we'll get there when we get there. How does error change before and after a measurement update? So E plus, this is the error after the measurement update, is truth minus X hat plus. Okay, which we've just said that X hat plus is X hat minus plus Kalman gain residual, right? So this is really X minus X hat minus Kalman gain Y minus H X hat minus. Okay. But this term here, so X minus X hat minus, this is E minus. So to clarify, our error after we update is our error before we update, and then minus Kalman gain, and then I'm going to expand this, right? Y is really HX plus nu minus H X hat minus. Okay. Now I'm going to rework some things. So our error after we update is our error before we update minus K, and then in parentheses H, and then in parentheses we have X minus X hat minus plus nu. And am I being lazy? I think nu does, yep, sorry. I'm getting lazy. This is a vector. Is that a raised hand I see, or are we doing okay?
The raised hand was about nu being a vector.
Yep, okay, cool. Thank you for keeping me honest. So now X minus X hat minus is our error before the update. Okay, so we're just reworking our terms here. So here it is again. Our error after the update, we want to get this entirely in terms of the before and after error. I don't want to talk about state. I want to say the after picture error is the before picture error minus K, and then we have H before picture error plus nu. Okay. And then I'm just going to rework this equation, just kind of algebraic manipulation. Finally, our error in the after picture is identity matrix minus KH error in the before picture minus K nu. Okay, so to be clear, this is error after update, and this is error before update. Okay, so how does covariance update work? Well, we substitute. So remember, P is going to be, remember, it's the expected value of X minus the expected value of X, and then expected value of all that stuff, right? In this case, our covariance after we're done with our update, so P plus, is the expected value of X minus X hat plus X minus X hat plus transpose. Okay? Which, if we go through and we say, okay, isn't X minus X hat plus, that's just our error, right? This is our after error. It's just going to be the expected value of our error times our error transpose. And this is getting busy. So there's a plus sign and then also a T, but you get the idea. So the after error times the after error transpose, expected value of that, that is our covariance. So let's go through and substitute in this equation that we just came up with. We'll say our covariance after the update, which generally we want to minimize. So we're doing this in a certain order here. You're going to see that first we need to set up an equation for what our covariance is, and then we'll need to say, okay, well, what is K? Because this whole time I've just been throwing this K term around. What is K that actually minimizes our covariance? That would be some sort of optimal estimator gain, but I'm getting ahead of myself. One thing at a time. Let's substitute. This is the expected value of, and then we've got I minus KH E minus K nu, and then that again, I minus KH E minus K nu transpose. Okay, here we go. It's time to FOIL this. P plus is equal to expected value of, okay. So first we're going to have I minus KH E hat minus, sorry, not E hat, just, ooh. Oh, wow, look at me go. In my handwritten notes, I switched from E's with vectors over them to E's with hats over them because I'm so used to writing hats over E's. So let me make a note here, no hats. Okay, I think the next time I go through and teach this, I'm going to come up with a different notation for this lecture. Apologies that you'll have to be guinea pigs. Let's see, this should be transpose, and then I minus KH transpose, and there's our first term. And then we've got our inner and our outer terms, right? So we're going to get I minus KH E minus, and then nu transpose K transpose. Okay. And then we're going to get minus K nu E minus transpose I minus KH transpose. And then finally, our last term is going to be K nu transpose K transpose. It's the expected value of all of that. Okay. Now, remember that expected value, it kind of shrinks and hones in on the things that are actually random in nature, right? So identity matrix is not random. Kalman gain is not random. H, our measurement sensitivity matrix, is not random, but there's going to be a random element to our error. There's going to be a random element to our noise. So it's going to be the E's and the news is going to be where the expected value operator focuses. So P plus is going to be I minus KH, and then we've got expected value of E minus transpose, and then we've got I minus KH transpose minus I minus KH, expected value of E minus nu transpose, and then we have K transpose. And then we have minus K expected value of nu E minus transpose, I minus KH transpose. And finally, we have K expected value of nu transpose, K transpose. Please tell me something in here cancels out. Anybody want to take a guess? At least one of these terms is 0.
Would the expected values of the one, so the E minus times E minus transpose, be 0?
Ah, so that one, so remember that the expected value of E plus transpose is P plus. So the expected value of E minus transpose, this is actually the old covariance. It's kind of been hiding in the equations this whole time. So the new covariance is the old covariance plus, but keep moving, look at the other ones. Is there going to be any correlation between your noise on the current measurement and the error before you process the current measurement? Those never talk to each other, right? So there'd be no, so we've got the old error in the state, and we've got the new error in the measurement, but the new error in the measurement doesn't impact the old state, it impacts the new state. So those are completely uncorrelated. This is 0. This is also 0. And then the last one, by definition, right, all the way up at the top of the lecture, we said expected value of nu transpose is R. So to summarize, our new covariance is going to be I minus KH times our old covariance, I minus KH transpose, plus K R K transpose. So this is going to be our covariance update equation. Covariance update. And then up here, we kind of skipped it. But this is our measurement update. Or sorry, our state update. So you might say, gosh, Paul, it took you the entire lecture to get through the state and the covariance propagate equations, but we've been talking for a half hour and we're already done with the state and covariance update equations. Don't worry, it gets a lot worse, but one thing at a time. So this is the equation that tells us what is our new best guess of our state if we have our residuals, which means we've taken a measurement, and this gain K. Well, there's the rub. We haven't talked about K yet. And then we have this equation here, which says, okay, once we're comfortable with our gain K, we have our old covariance. Remember, we talked about this back in lecture, the end of lecture 11. P is how much we don't trust our state. R is how much we don't trust our measurement. And so I'm saying if we have how much we don't trust our measurement and how much we don't trust our state before, here's how much we don't trust our state now. So we've got kind of the before and the after picture here. Okay. Now, just for your reference, this equation has a name. This is what's called the Joseph form. Of the covariance update. Which is definitely the one that I prefer. It's more stable, but it is also more computationally expensive. This is also valid for any K. It enforces symmetry. Okay. So now we said, okay, What order do I want to do this in? Let's talk about the Kalman gain next. We've skipped it for too long. It's finally time to go back and talk about the Kalman gain. Okay. So the whole point of the Kalman gain K is to minimize our error, right? So we want K to minimize the mean square update error. Whenever I say the word minimize, everyone's probably thinking, oh, are we about to create a cost function? And then that cost function is going to be something that we have to take the derivative of and then set that equal to 0. And yes, absolutely. And it's going to be a whole page of math. Buckle up. Here we go. So we're going to want the minimum of some cost function j, which takes in the Kalman gain k. And I'm not just kidding. And this is the expected value of our after error multiplied by itself. After error. There it is. So the after update error multiplied by itself. So basically the after update squared. And then we're saying on average, we want this to be as small as possible. Okay, so now one thing we can do, the first of many tricks that you'll see us performing here, is we're going to minimize j of k, which is equal to the expected value of the trace of E plus transpose E plus. Because remember, E plus transpose E plus is a scalar, so you can take the trace of a scalar and it doesn't make a difference. But what's cool is min j of k is that the trace of a vector times a vector is the same as the trace of a vector times a vector if you swap the order by cyclic permutation. So what I mean by that is we're allowed to make this move, E plus transpose. Okay? And also, the trace and the expected value operators are linear. You can actually swap the order of those and get away with that too. So this is the same thing as the trace of the expected value of E plus transpose. And maybe you see where we're going with this. The expected value of E plus transpose is the covariance. So minimizing our mean squared update error is the same thing as minimizing our covariance, or to be more precise, the trace of our covariance. So same thing. Are we trying to minimize our error, or are we trying to minimize how much we don't trust our state? Well, because how much we don't trust our state is a function of our error, it's kind of the same thing. Okay? So that's our goal. We want to minimize this thing. Here's the problem. P, specifically P plus, is itself a function of K. So we have some substitution to do. Okay. So before we do that, I want to point out first, let's review some useful properties. Okay. From the matrix cookbook, I should say. From the matrix cookbook. All right. Number one is that the derivative with respect to x of the trace of some matrix F times x is going to be F transpose. These are just by fiat. I'm just telling you these things. The next is the derivative with respect to x of the trace of fx transpose is f. Okay. And then number 3 is the derivative with respect to x of the trace of x f x transpose is going to be x f transpose plus x f. Okay, we're going to need all these in a moment here. So remember, our problem that we're trying to solve is the minimum of some cost function of the Kalman gain, and that cost function is just trace of the covariance. But the covariance is this, so we're going to have to go through and substitute. So we can find k through substitution and applying first differential condition. Okay. So the derivative with respect to k of jk, which is the same thing as the derivative with respect to k of the trace of p plus, is equal to 0. So set up and solve this equation and we will have our gain k. Okay, but remember that p plus is really that I minus kh p minus business, right? So what we're really saying is derivative with respect to k of the trace of I minus kh p minus I minus kh transpose plus k r k transpose equals 0, which we're going to need to FOIL this out. So we're going to end up with 5 terms, right? First, outer, inner, last, and then k transpose rk. So this is going to be the derivative with respect to k of the trace of, okay, let's walk together. I times p minus times I is just going to be p minus. Okay, and then we've got our inner term. This is going to be minus p minus h transpose k transpose, right? Because remember, the kh transpose is really h transpose k transpose when you distribute. Next is going to be minus kh p minus. And then finally, you're going to get plus kh p minus. And then we've got h transpose k transpose. Finally, we've got plus k r k transpose. And all this equals 0. Okay, here we go. Next, I'm going to distribute. So what we're saying is derivative with respect to k of the trace of p minus derivative with respect to k of the trace of p minus h transpose k transpose minus derivative with respect to k of the trace kh p minus plus derivative with respect to k of the trace of k h p minus h transpose k transpose. Finally, derivative with respect to k of the trace kr k transpose equals 0. All right, so far so good. So some of these are going to be really easy. Matter of fact, the first one's going to be really easy. Derivative with respect to k of a term that doesn't include k is 0. The other ones, we're going to have to refer back to those rules that I have at the top of the screen here. So we've got some stuff multiplying k transpose. I think that this term reminds me of number 2 up above. And so by that same logic, if we're following that this is number 2, then what we should get is just p minus h transpose. but we have to keep the minus sign from up above. Okay. So far, so good. So then follow along with me here. I think this looks like number 1 up above, but only after we do a cyclic permutation. So this is the same thing as minus d dk trace of h p minus k. Right? Remember, we're allowed to do cyclic permutations within a trace. And this, I guess I should kind of stay locked in on that top part. By virtue of rule number 1 up above, is going to be negative, I think it's just, yeah, P negative transpose H transpose. Okay, and now I realize this is dangerous. This is not P to the power minus transpose. This is P minus transpose. So I guess I should put parentheses on that. Okay, next is, let's see, we've got Kalman gain times some stuff times Kalman gain transpose. But as a matter of fact, here we have Kalman gain times some stuff times Kalman gain transpose. So I'm actually going to combine these terms and say that this is derivative with respect to k of the trace of k, and then in parentheses, h p minus h transpose plus r. And then we've got k transpose equals 0. And now this reminds me, by number 3, which number 3 is saying xfx transpose is going to become all this other stuff. So what we're going to end up with here is k, and then we've got h p minus h transpose plus r transpose plus k h p minus h transpose plus r, which is symmetric. So the transpose doesn't really matter here. Also, I should take a note. I found a typo in my handwritten notes. There it is. Fixed it. Okay, so let's combine some like terms here. Ooh, do I have... Oh, because that's symmetric too. Okay, sorry. I'm just looking at the next step in my notes, and I wanted to make sure I didn't screw something up. So we kind of have the wreckage of a battlefield here, but if we combine all of our terms, we're going to end up with negative 2 p minus h transpose plus 2 k h p minus h transpose plus r is equal to 0. Okay, all we're doing is combining all of our terms. Thankfully, we get a mercifully short equation after all this. And so if we move this over to the other side of the equal sign, and I'm going to skip a couple of steps here, you can see how this is going to end up being that k times some stuff is equal to p minus h transpose. And so then if you right multiply by the inverse of some stuff, then what you'll get is that k is equal to p minus h transpose h p minus h transpose plus r inverse. And this gets a box. This is the all-important Kalman gain. So the Kalman gain is not just a number. We don't just tune the Kalman gain. The Kalman gain is computed to be optimal in how it minimizes our covariance. There is not a better gain to minimize the covariance of a linear system. Okay. Now, what we can tune, I mean, Kalman filter tuning is its own whole discussion, but The Kalman gain is something that you can compute by a recipe. There's a formula for this. We don't guess and check at it. Right? Now, there will be, kind of baked into this, there's the uncertainty in R, which is our measurement covariance, and then there's the uncertainty in Q, which is our process noise covariance. Those are going to be things that we try to tweak to change the behavior of our filter, right? So that's, then you get into kind of the black magic of filter tuning. But for now, this K is the Kalman gain that goes into this equation and this equation, which is our state update and our covariance update. And then in the last lecture, we talked about the propagate steps. So we're done with Kalman filters, except not really. We're about halfway through, but we're done with kind of the bare minimum linear system Kalman filter. Now, before we wrap up this discussion, I want to do a quick sidebar convo, show you one other derivation of what's called the collapsed form of the covariance update, just for your awareness. But these are kind of the preferred equations that I recommend. Before we get there, any questions? We're feeling okay on update and Kalman gain? Okay, let's keep pushing and then we'll take a break. So there is also, say, we may develop a more compact form of the covariance update. Okay, so remember, we said that P plus is equal to I minus KHP minus I minus KH transpose plus KR K transpose. Okay, and if we actually go through and multiply this out, we get that P plus is going to be P minus minus P minus H transpose K transpose minus KH P minus plus K, and then in parentheses, H P minus H transpose plus R, and then this is going to be K transpose. Okay, so now this is where we are going to plug in Kalman gain selectively. So not every term. Okay, so bear with me for a long equation. P plus is P minus minus P minus H transpose, oops, started to write R, that's a K, minus KH P minus. But now, for this kind of ugly term towards the end, we're going to plug in plus P minus H transpose, and then we have H P minus H transpose plus R inverse, and then in parentheses, H P minus H transpose plus R, and then we've got H P minus H transpose plus R inverse H P minus transpose, which these two cancel out through the identity matrix. Okay, is that going to make our life easier? Well, we'll see. So then the next bit is we're going to say, oh, by the way, this K we're also going to plug in. So we're going to get P plus is equal to P minus minus P minus H transpose K minus P minus H transpose H P minus H transpose plus R inverse H P minus transpose. Okay. Plus, now it's this term from here, P minus H transpose identity matrix, which we don't bother to write, H P minus H transpose plus R inverse H P minus transpose, which all of this cancels out. So what we're left with is just the new covariance is the old covariance minus P minus H transpose K. Oops. Transpose. Okay, which is the same thing as, oh, did I screw something up?
Sorry, is there a transpose missing on that previous 8K HP minus term in the
Help me out.
first equation?
Let's see, first
It
equation.
just mysteriously occurred here in the end of, unless I'm reading something wrong, at the end of that term where you plugged it in.
It's this bit, right? There's the K transpose, or did I
Yes,
make it some
wait,
silly
in the
mistake?
next, so when you go negative KHP minus and then plug in the K gain, where does the P minus transpose come from? Because previously it's just P minus. Oh, it's because you're multiplying P and P. Is that it?
Clearly there's a lot of P's going on here. Let's see. So in this equation, get my highlighter out. Stop me when I find the thing that you're confused about. Over here? In the last term?
Wait, did not see your highlighter at all.
Oh,
I'm
sorry.
looking at the second term in the equation where you pointed the arrow to. Well, the third term in the equation where you pointed the arrow to. That
Okay.
last P minus.
This term right here.
Yes.
Let's see. So that is K H P minus.
Yep. And then when you
then
plug in the K.
Oh, you know what? Did I? Hang on. I did make a mistake. Hang on. I'm plugging in for this K. Sorry, good catch. Hang on. So this K. Oh, but then why is this P transpose there? Is that what you're saying?
Yeah. Why does that P suddenly
not.
become transposed? The only
Oh,
explanation I can think is because you're multiplying by
doesn't.
P.
Nope, it doesn't. I made a mistake. However, P is symmetric, so transposes don't matter. So my mistake. So we're plugging in for this term. This should not have a transpose, which, I mean, it doesn't. You can put it there. You can not put it there. But that will sort itself out. But yep, that K becomes this. Are we good? Thumbs up?
Good now.
Okay, cool. Thank you for keeping me honest. Okay, we're almost done. Take a break in a minute here. So P plus is equal to P minus minus P minus H transpose K transpose, which is the same thing as P minus minus K H P minus, or we could just say P plus is I minus KH P minus. And this is what's referred to as the collapsed form, as opposed to the Joseph form of our covariance update. So this is collapsed form. Okay. However, I will mention, you should know this for your awareness, but this is not recommended. Because it does not guarantee symmetry. And kind of invites numerical issues. Okay, so now we have our Kalman gain, we've got the collapsed form of our covariance update, we've got the Joseph form of our covariance update, we've got our state update. All of this is built on the back of being able to propagate our state and propagate our covariance. So we have those equations. So we have everything we need to assemble our Kalman filter. So what we're going to do is we're going to break there. I think this is a nice natural stopping point. And let's see, it is 7:03, really more like 7:04. Let's take a break and come back at 7:09. And that is when we will go through kind of a summary of the Kalman filter up to this point. Okay, take a break.
If you're okay for a quick question about the second derivation for the collapsed form.
Yeah, what about it?
I didn't really get the point of substituting k's in a bit at a time instead of going all out and just substituting all the k values. Would that give a different result, or would it just be difficult to factor?
Just to fit it all in one line.
Okay.
That's all it was. Yep.
Makes sense.
All right, welcome back, everybody. So I want to go through and summarize the Kalman filter up to this point because it's been a minute. Then we're going to talk about some practical applications, and then we will break for the day. And then tomorrow, I've kind of already hinted at this tomorrow. Next lecture is the nonlinear Kalman filter, because we've been talking about the linear Kalman filter, one thing at a time. So this is our Kalman filter summary. Try to fit this all on one page here. Here's how we do this. So you would initialize at t equals 0 with x hat k minus 1. So this is at the old time after updating, which doesn't really make sense. This is just, it needs to start with something. It's like a chicken and the egg problem. We're going to start off by saying this is just 0. And then similarly, p k minus 1 plus is just p naught. So you need some initial state and some initial covariance to get your filter started, sort of like trying to start up a lawnmower, right? Then we gather a new measurement. At time tk. So at time tk, you've got a measurement yk, which comes along with measurement uncertainty or measurement covariance rk. Next is state and covariance propagate from the old time to the new time. So we'll say tk minus 1 to tk. So how do we do that? Well, remember that phi tk minus 1 tk minus 1 is just the identity matrix. Phi dot tk minus 1 to tk is f of t b tk minus 1 to tk. Okay, that gives us our, so we would assess these to get our state transition matrix. Then the next is going to be x hat minus at time k is phi tk minus 1 to tk x hat plus at the old time. So we move from updated to propagated, but we're moving forward in time. And then similarly, p k minus is going to be phi tk minus 1 to tk p plus k minus 1. And then we've got phi tk minus 1 transpose plus qk. And then I'll say, or you can use the ODE int method, which would look like x dot of t is f of t x of t, and then p dot of t is equal to f of t p of t plus p of t f of t transpose plus g of t q of t g of t transpose. Okay, those are your options when it comes to state and covariance propagate from old time to new time. Then you've got state and covariance update. At time tk. Okay. This is going to have 4 steps, so we'll kind of enumerate these. A is compute the measurement sensitivity matrix HK. You might say, isn't H going to be a constant for this problem? It's like, yeah, if you're only processing one measurement. But in general, you're going to get different measurements at different times. So on homework 5, you're going to get range rate, and bearing measurements. So you're going to need 3 different measurement sensitivity matrices. It's going to get a little complicated. So you'll need to choose the right one. Then we compute the Kalman gain. Which is going to look like K at time K is PK minus HK transpose. So I left out the K's during the derivation because this is going to get really annoying. HK, PK, HK transpose. Oh, and this is minus. Plus RK inverse. And then we update state. Which is going to look like X hat plus at time K is X hat minus at time K plus Kalman gain, and then we've got measurement at time K minus residual, which is just what we expected our measurement to be. Sorry, it's not measurement minus residual. All of this is the residual, which is measurement minus expected measurement. Apologies, I misspoke. Okay, finally, update covariance. So this is going to look like PK plus is equal to I minus KK HK PK minus I minus KK HK transpose plus KK RK H. Oops, not H. Someone's getting tired. KK transpose. Okay. And then all of this, when we're done, is then when we loop. And so we'll say K equals K plus 1. And there's our flowchart loop. So we gather a new measurement at time K. At that instant in time, we go, okay, what is my prediction? And then what is my correction? Or what is my propagated state? And then what is my updated state? And that's pretty much what we have. So this is just a summary of the equations that we've already been looking at. So Kalman filter summary. Questions on that? Okay, cool stuff. So next thing I want to talk about is Kalman filter considerations. Process noise is one of the most misunderstood and misused parts of a Kalman filter. Okay. First of all, I'll say recall that QK does not equal Q of T. Right? Remember we talked about that before. So 2 ways of considering our covariance propagation. The first of those we'll talk about is the ODE int method. So we have P dot of T is F of T, P of T plus P of T, F of T transpose. plus G of T, Q of T, G of T transpose. Boy, that just fit. Where the expected value of our process noise, remember that's omega of T transpose, is going to be Q of T Dirac delta. Oops, I got ahead of myself here. This shouldn't be a T. So omega of T, omega of epsilon is Q of T Dirac delta T minus epsilon. Okay, so that is to say that our noise is completely uncorrelated with itself in time, but at a given time, then the noise correlation with itself, the noise covariance or the process noise covariance matrix is this Q of T. We also said that PK is phi K P K minus 1. Is that the way our equations had it before? Yes, okay. And then phi K transpose plus QK, where QK is the integral from TK minus 1 to TK, phi epsilon to TK, G of epsilon, Q of epsilon, G of epsilon, transpose phi from epsilon to TK, transpose the epsilon. Okay, this is where I want to be abundantly clear. This Q and this Q are not the same. This Q and this Q are the same. So we don't want to get that confused. There's two Qs floating around here. Okay. So generally, we prefer, or at least I prefer, the state transition matrix method to the ODE int method. So we'll need to make friends with QK. So I want to make QK make sense. And I think the best way to do this is through an example. And that example is going to take us about 1 or 2 more pages to get through, and then that'll be it for today, because we've learned a lot. And then next class should, in theory, be a little bit shorter. Next class is we're going to take our Kalman filter equations, and then we're going to modify them for when the system is nonlinear, and that's actually going to be what you need for the homework. So technically for homework 5, we're not ready yet. We will be ready at the end of next lecture. Okay, but just pausing here for questions. Okay, let's do an example. So KF example. Tracking position and velocity. Okay. Consider a vehicle floating in space subject to random white noise acceleration. So this is not quite the system that we're talking about on homework 5, because homework 5, it's going to be subject to two-body motion and random white noise acceleration. But we'll start with a simplified model. So x dot is fx plus g omega, where omega is just acceleration. That's what we're saying here. Okay. In state space, we'll say that, think of it this way, r dot of t, so velocity, and then r double dot of t, acceleration, so velocity and acceleration, is equal to, let's go through and fill in our system here. Our state is going to be position and velocity. Okay, so let's think about it. Our velocity is just our velocity, right? So our position is not part of that equation. So this is going to be 0 identity matrix plus, we're not assuming there's any perturbations to our velocity. We're assuming the perturbations are to our acceleration. Okay, so velocity is velocity. That's the trivial one. Now, in this problem, and now on the homework, it won't look quite like this, but this is a good starting point. In this problem, we're saying our acceleration has nothing to do with our position. It has nothing to do with our velocity. It is literally just noise. Okay? So now, for this problem, we know that Q of t is just going to be sigma omega squared times the identity matrix. And we'll also say, typically, Q of t is diagonal. And QK is not. Okay. Also, from the above, we can say that phi from tk minus 1 to tk is what? And we're kind of skipping some steps here, but basically following the state transition matrix math that we did several lectures ago, you can convince yourself that this is the case. But it's going to be identity matrix. It's going to be tk minus 1 times the identity, where you could just write this as delta t, 0, and identity. So qk is the integral tk minus 1 to tk of phi epsilon to tk. Gosh, we have this memorized because we wrote it so many times the other day. Q of epsilon, G of epsilon transpose, phi epsilon to tk transpose d epsilon. Okay. Let's go through and actually plug some stuff in here. So we just said that for this problem, we're assuming that our process noise is just Gaussian white noise with our process noise covariance matrix is sigma omega squared times the identity matrix. So you can say that this is equal to sigma omega squared integral tk minus 1 to tk of phi epsilon to tk G of epsilon transpose. Really, there's an identity matrix in here, but we can ignore it. Phi of epsilon to tk transpose d epsilon. Okay, so let's go through and break this up piece by piece. So let's break this up piece by piece. Where phi from epsilon to tk times g of epsilon. Let's make that make sense. Well, that's going to be identity matrix, and then we've got the identity matrix multiplying TK minus epsilon, 0, and then the identity matrix. And this multiplies 0, and then the identity matrix. Which, okay, rows of the first, columns of the second, is going to give us identity matrix TK minus epsilon, and then just identity matrix. Okay. So now from here, we've got phi epsilon TK, G of epsilon transpose, phi TK epsilon transpose. Well, that is just the same thing as identity matrix, TK minus epsilon, identity matrix, and then we've got identity matrix, TK minus epsilon, identity matrix. And so this should fill out into a square matrix, and it does. And what we get is identity matrix, TK minus epsilon squared, identity matrix, TK minus epsilon, identity matrix, TK minus epsilon, and identity matrix. Okay. This is then what is integrated from TK minus 1 to TK. So we can split this up into 4 integrals. And yes, we are doing calculus today. I'm amused that the math in this class has gotten so gnarly that it's like, oh, thank God, it's just calculus. We can do that. So let's see. Integral TK minus 1 to TK. And then we've got TK minus epsilon squared, identity matrix, d epsilon. Okay, this is going to be, ignoring constants of integration for now, 1/3 TK minus epsilon cubed times the identity matrix. Okay. Similarly, the integral TK minus 1 to TK, TK minus epsilon, not squared, just regular, times I, the epsilon, ignoring constants of integration for now. This is going to be 1/2 TK minus epsilon squared I. Okay. And then similarly, integral TK minus 1 TK, just the identity matrix, is going to be TK minus, sorry. This is TK minus 1. And then this is also TK minus 1. I forgot to substitute back in. There we go. Which, if we're feeling lazy and we just want to say that that is delta T, then we can simplify and say that QK is equal to sigma omega squared. And then we've got 1/3 delta T cubed identity matrix, 1/2 delta T squared identity matrix, 1/2 delta T squared identity matrix, and then just delta T identity matrix. And I guess these are associated with time K. There it is. So this is one example of how to build QK from Q. Cool stuff. Questions on that? You will do something similar on homework 5. All right. Last topic, and then we'll break for the day. I want to talk about, and this is really just for your information. This is not strictly necessary for homework 5. Modeling of sensor biases and other parameters. Okay. So biases are fixed values. This is just how much is the sensor wrong every single time. They're fixed values, so you may be tempted to model them as constants. Do not. So we might remember this from our discussion of inertial navigation. We model biases as Gauss-Markov processes. So a Gaussian process is one in which all PDFs, probability density functions, describing it are Gaussian. And a Markov process is one whose PDF now depends on the previous state. Okay, so combining these, a first order Gauss-Markov or Fogum process is a first order differential equation with an evolving Gaussian PDF. So the way we write this is x dot of t is negative beta x of t plus omega of t, where omega of t is Gaussian white noise, having an expected value t is equal to 0, and expected value of omega of t, omega of epsilon transpose is equal to sigma omega squared times the identity matrix times delta t minus epsilon. Okay, so the first term, we have basically an x dot equals negative x problem. That generally tends to push itself back to 0. That's actually going to be a negative exponential decay problem. And then the omega term is your random walk. So that's saying, oh, the derivative of my state is random. It's going to go off in a random direction, but it's also going to tend to want to nudge back towards the origin. So for beta equals 0, this is simply a random walk. Okay, for beta is a positive number, then the current derivative is a function of the state and random walk. So there's still going to be some random kind of wonkiness to it. Correlation time is defined as tau is equal to, actually is defined as 1 over beta. And the solution to our bias term is of the form x of t is x of t naught, exponential function negative beta t minus t naught, plus the net effect of all that noise. So the integral from t naught to t, omega of epsilon, exponential function of negative beta t minus epsilon, d epsilon. So the mean is computed as the expected value of our bias term is equal to the expected value of x at the initial time, exponential function, negative beta t minus t0, plus the integral t naught to t, expected value of omega of epsilon, and then expected value, sorry, there's expected value and then exponential function. I knew I was going to make those up at least once. Negative beta t minus epsilon, the epsilon. Yeah. Which the expected value of our noise is just 0. So on average, we expect our bias term, or our first order Gauss Markov process, to be the expected value of the initial, however it started off, and then just that decaying back towards the origin. So exponential of negative beta t minus t naught. And there's other information we can share about modeling our first order Gauss Markov stuff, but I think that that is probably plenty for this lecture. So why don't we stop there? And next time we will talk about the extended Kalman filter. And if we have time, we might even talk about the unscented Kalman filter, which is another variation. Different ways of handling the nonlinearity in a real dynamics problem. But before we break, any Kalman filter questions? Okay, well, with that, I will stick around if anybody has any questions specific to this class. Otherwise, everyone is dismissed. Hope you have a great weekend.